wait for him. So welcome to this new webinar. And probably, as you know, this one is the new series of webinars, of very short webinars, the SnacTKO, where we're going to present all the new features for the new releases, okay, all the new minor releases. This is the first one. As you know, right now we are in version 1.1.4, and by next Friday we will release version 1.1.5. And I'm going to show you the new features that you can find in this new version by the end of this week. So I'm going to share my screen. Here we are. Okay, so there are many new features. You will see the change log with the new version, but the most important one is the beam diagram plot. It's something that can be found very easily in many commercial softwares. It took some time for us because the way OpenSees gives the results for beams is quite strange, so we had to work a little bit on it. And I'm going to show you how it works. Now, this one is a very simple model, okay, just a very simple building, 1 floor, 1 bay. And up to now, so up to version 1.1.4, the only way you had to visualize results on beams were, let me go in full screen. Here we are. So the only way to visualize the results on beams is through the surface color map or the Gauss plot. Okay, and the surface color map, you can visualize 2 kinds of results for beam. As you know, in OpenSees, the results on the beam can be either on the beam nodes, like for example, the local force or forces, or on the element Gauss points, like section force or section deformation. Okay. Now, in the surface plot, you can visualize both of them. If you choose to visualize local forces or the global forces, what you obtain is actually something that is quite strange, and many users are always asking, why do I see results with different signs? So for example, in this case, it is the axial force. Of course, here you have axial force on the beams because there is the rigid diaphragm. But as you can see, for example, here the axial force should be constant, and the value in fact is constant, but the sign changes. Here it is positive, here it is negative. And it makes perfectly sense because this kind of result in OpenSees, it refers to the element internal forces at the nodes, so they have opposite sign. So it is not so easy to visualize the results in this way. Otherwise, you can visualize the results on the Gauss points. Now, if you visualize the results on the Gauss points directly on the surface color map, what you obtain is kind of an interpolation of them. For example, if I show the bending moments, but then you always have the same problem. Okay, so if you choose the surface color map, if you choose the results on the Gauss points, you don't have the problem of the sign. If you choose the results on the element node, you have the problem of the sign. Okay, so the values are correct, but the sign is inverted at certain nodes. So you may say, okay, well, I always choose the section forces, but then with the section forces, you have another problem. For example, if you look at the components here, if you do not use a section aggregator, you will never be able to visualize the shear in the section forces. While if you look at the element forces, there is always shear, as you can see here in the components, because of equilibrium. Okay, so now the new option that you have in STKO version 1.1.5 is to create the beam color map, the beam diagram plot. You can either create it here on the context menu or the work tree, or directly on the ribbon bar, which is this one, beam diagram plot. Okay, so the beam diagram plot is a plot that works only for results on beam elements. So for example, here you can visualize only the results that belongs to a beam element. So for example, local forces, which is a result, as I said, on the element nodes, or section forces and section deformations. Okay. Now, if I choose a result like nodal results, so local forces, what I obtain is actually a linear interpolation of the results from one node to the other. So, for example, if I look at the bending moment. Okay, let me go to the static stage, to the vertical stage, so it's easier to visualize. Okay, and moment about Z, and moment about V. Okay, here we are. Let me make it smaller. Of course, you can work on it. You can change some settings. So this is perfectly fine. The only problem is that, as you can see, the sign is automatically inverted, because this kind of plot already knows that this kind of results has the problem of an inverted sign on one of the two nodes of the beam. So it takes care of inverting the sign. So the sign now is perfect. The only problem is that this kind of result is only stored at the element nodes. So at most, you can have a linear interpolation between them. Okay. So in this case, for example, I divided, if you go on the preprocessor and I go to the mesh, I divided each member in two elements. That's why you can see a result in the middle. But if you do not discretize the element, you will not see any result here. You will just see a linear interpolation from one node to the other. Instead, for example, if you choose a result on the Gauss point, it is more accurate in the sense that a single element has more Gauss points. So if you look at the bending moment now, you will see that every element has 5 integration points. Let me switch off the beam extrusion so you can see it better. Has 5 integration points. So here I have 5 sampling points here and 5 here. So it's more smooth. And the nice thing about visualizing the results on the Gauss point is that you can actually see during the loading history how this diagram changes. And this is something that you cannot find in many other softwares. So for example, let me do an animation of this one. And let me put some deformation here. Okay, let me show the beam extrusion. And just 15 should be fine. So this actually is a vertical load plus an horizontal load later on. So if you do an animation, you can see how the bending moment changes due to vertical loads. And then there is the formation of 2 plastic hinges on the 2 corners here. Probably the formation is too much now. Let me make it smaller. Okay, now in this case, I'm using a force-based element. So as you know, the force-based element has a correct interpolation of the forces, okay? And the nice thing is that, for example, if you want to visualize the deformation, you will see actually how a force-based element works. So this kind of plot is also very useful to understand what's going on inside the element. For example, if you choose instead of section forces, I want to look at section deformation. As you may know, for example, in this case, the bending moment will be almost linear due to the lateral load because of equilibrium. But if the moment is linear here, and there is a plastic hinge at the 2 corners, I will see a concentration of deformation at these 2 Gauss points. And this is actually what happens. So for example, if I go in section deformation and I visualize key Y, which is the curvature about the local Y-axis, you can see that at the end it is almost 0. And then there is a high value here at the last Gauss point because of the strain localization. So the formation of the plastic hinge. If you do an animation, you will see that at the beginning it is almost constant, then almost linear, and then little by little it starts forming a plastic hinge here, and finally also here. Okay, and this is pretty nice to understand the difference between, for example, a force-based and a displacement-based element. So, for example, if I do the same with a displacement-based, you will see a completely different result. The displacement-based element actually you will never see that localization in a single Gauss point. You will see instead a linear curvature here because the displacement-based computes the curvatures directly from the displacement. And you will see a flattening of the bending moment, which is not correct. But as you know, it is the drawback of a displacement-based. So let's do this test. I go here and I change the element from force beam to displacement beam column, 3D. Okay, and I just run the analysis again. Okay, vertical and horizontal analysis. Back to the post processor, and I reload the results. Now, as you can see, it is very different. If I do an animation of the curvature, you will see that there is not a localization at the ends, at the 2 ends. Okay, as you can see, they are linear now. and then they start localizing. Here you see a little discontinuity, but it makes sense. It is a drawback of the displacement-based formulation. While instead, if you look at the bending moments, you will see something strange, which actually makes sense, but it is not physical. You will see a flattening here because in the displacement-based element, the curvature are computed from the strain. But when these sections actually fail, the bending moment will not increase, so it will be flat here. Remember, this is not real, but if you use a displacement-based element, you need to discretize it. Now, the nice thing about this kind of plots, when they are plotted at the Gauss point, is that you can really understand what's going on inside the finite elements. Okay, so here it is what happens with the bending moment. So almost fine at the beginning. Then when it goes into a nonlinear stage, you will see something that is not completely correct. Okay, and this is fine. This is drawback of the displacement-based element. Okay, so this one is the main new feature of version 1.1.5. And it is pretty easy to use. So it is like any other plot. So you can choose the source database, the model stage, the result. Now, as you can see, we renamed the results. So you can see also a nice name for the components. And you choose the component, the deformation, and so on. And down here, you have one extra option that allows you to scale this plot. Okay, if you want to make it larger or smaller. Okay. And so this one is the main new feature of version 1.1.5, and as I told you, it will be online this Friday. So okay, so by the end of this week, and then we are also working on a completely new major release, which is version 2.0. And this new version will have a very new feature, which is the Python script environment for both the pre and post processor. So now you can do many more things. For example, in a post-processor, you're not limited to visualizing the results or extracting the results at certain points. You can actually manipulate the result, okay, to create your own result. Now, I will talk about this new feature later on, but I want just to give you a very small preview, okay? So this is all about the beam diagram, and I want to show you this new preview for what will be version 2. Okay, now just let me open another kind of result for this demonstration, and it will be a shell this time. I want to switch off the grid, I don't need it. Okay, so this one is a simple shell loaded in the middle with a pressure load. Okay, and this one was made with a damage model. So if I try to visualize the fiber, a new feature actually in this new version is that now fibers are not limited to points of the same size as it was before, because before it was a constant size for every point. Now you can actually choose how to scale them, pretty much like the Gauss point plot. Okay, so in this way you can visualize the fibers that are more important. Okay, so for example, in this case, I'm showing the damage. And of course, I want to visualize the fibers with the higher damage variable instead of those which are pretty elastic. Okay. Okay, so I just want to show you what's going on in this shell. Okay, it starts, everything is elastic, and then little by little, the two cracks starts forming. Okay, let me also include some deformation. Okay. And let me do an animation so you can see what's going on here. Okay, so what is a damage variable? A damage variable is a number that says how far a material point has gone into a nonlinear state. So 0 means the material is still elastic. 1 means it is completely broken, and then there are values in between. Okay. Now in the new version, you have a very new feature, which is this one, the script editor. Here you have a very small MATLAB-like environment, where basically here you have a script explorer where you can choose the location for your own scripts. All the scripts are, of course, in Python. And here you have the script editor, where basically you can write your own Python scripts. You can save them, you can change them, of course, and then you can run the script. And in this script, basically, you can actually interact with the document itself. So instead of going here and creating everything manually, you can actually create some scripts to make some automatism. But the nice thing is that now you can access the database and you can actually create new results. So for example, this is a very simple example. If we look at this original database and I look at the results on the elements, here I have the section fiber damage. Now, as I said, and as you can see here, this variable goes from 0 to 1. Now, to make it clear, I actually want to put the same size so you can see the color variation. Okay. Now, as you can see, these values, let me make it smaller so it's even easier to visualize. As you can see, these values varies linearly from 0 to 1, so from blue to red. But let's say you want to visualize a new result, a result that is not the actual damage, which is this one, but you want to visualize a result that says, okay, for me, the damage is in a critical state if it is larger than 0.9. And it is in a warning state if it is in between 0.5 and 0.9. Everything below 0.5 for me is acceptable, okay? So you can write this kind of derived result in this way. So I say D1 is equal to damage larger than 0.9 times 1. So every point that has a damage variable larger than 0.9 will become 1. And all the others 0 in this first component here. Then in the second part of the equation, I will make all the points here with a damage variable that goes from 0.5 to 0.9 equal to 0.5. And all the others are 0. So when I sum them, basically all the points with a damage variable larger than 0.9 will have the value of 1. And the values in between 0.5 and 0.9 will have a value of 0.5. All the others will be 0. Okay. So I do this one. And then I can add it to the original database. So now when I run the script, you will see that here you will find a new result, which is actually this one. And I decided to call this one critical damage. And then you can actually plot it. Okay. So let's run the script. Here you have the critical damage. And then you can go back in your fiber plot. You go in the editor. And you choose, instead of section fiber damage, you can choose critical damage. And now, as you can see, you have only these two kind of values. Okay, red, where it is larger than 0.9, and green, where it is from in between 0.5 and 0.9. Everything else is 0 for me. So this actually is very useful to visualize, to create results that are not in the original database, so results that you cannot get from OpenSys, but they are custom results, so results that you can create based on your needs. This is very effective. Now, of course, there are many other more things that you can do with the scripts, because you can actually extract the results, you can write them on a report, you can do whatever you want. And we will spend many other webinars talking about this, because of course we cannot do it in a couple of minutes. But this is all. Basically, this one instead will be the feature for version 2.0, which will be a major release. Okay. Yeah, for example, you can do verification, code checks, share flexure, drift, etc. You can do basically whatever you want, because when you have the capability of accessing the database and creating custom results, inspecting them and working with them, you actually have an infinite number of possibilities. Okay, so you're not bound to the results that are available from OpenSys. You can actually work with them, which is pretty much what majority of researchers now do, just by passing the results of OpenSys to other tools such as MATLAB, for example. But now the nice thing is that everything is embedded into a single software. Okay, so you can create your own results, you can post-process your results as you would do with MATLAB, but you can still actually visualize them in SnacTKO. So we think that is a very, very exciting feature. Okay, so I think it's everything for this short webinar. I think we have some minutes for questions. So if you have any question, please feel free to ask. And thank you everyone for joining this webinar, of course. Oh, thank you, Marco. Oh, let me stop sharing. Okay, so as I said, this new version will be online on Friday. Okay, it will be Friday 27, so at the end of this week. So if you have already a license for SnacTKO, you can just download the new version. The license, of course, is not bound to the current version. Okay, so you can actually update your SnacTKO version. There is no problem. And then in a couple of weeks from now, we will release the major release, which is version 2.0. Okay, so I think there is no question from the participants. And well, thank you everyone for joining this webinar. And don't forget to subscribe for the next webinar, which will be in December. And it will be about eigenvalue and response spectrum analysis. Okay, so I think this new webinar will be quite useful for many users. So thank you everyone, and see you on the next webinar.